Okay, so hello and welcome back. So in this video we want to do example number 20, which is consider functions f and g. Consider functions f and g such that composite GOF is defined. Composite GOF is defined and is 1, 1. Meaning that GOF is, well, injective. Are f and g both necessarily 1, 1? Are f and g both necessarily 1, 1? So what we have here is that we have two functions f and g in such a way that the composite GOF is defined and is 1, 1. So GOF is 1, 1. So are f and g both necessarily 1, 1? Meaning that suppose that you have this function, for example, you have, for example, 3 sets over here, a, b, and c. And suppose that, for example, f is a function that goes from a to b, and g is a function that goes from b to c. Now suppose that both of these functions are 1, 1, and they are defined in such a way that, for example, we have these, that, for example, this is mapped to this one, and this is mapped to this one, and this is mapped to this one, and this is mapped to this one. On the other hand, under G, basically this element is mapped to this one, this element is mapped to this one, and this element is mapped to this one, and this element is mapped to this one. And then, of course, you can say that GOF is a function that goes from A to C. This is GOF. And then under GOF, A is mapped to C. And this one is mapped to this one. And this one is mapped to this one. And this one is mapped to this one. And as you can see, GOF is 1, 1. Now what we are asking now we can see that what we know is that GOF is 1, 1. Meaning that every element of A every distinct element of A has a distinct image in C. Now, is it necessary for f and g to both be basically 1, 1 so that GOF can be 1, 1? Is it necessary for f and g to both be 1, 1 for that to happen? Now, in order to answer that question, we need some missing information that we don't have in terms of basically in terms of some theorems. And so as an example, so we cannot think logically about that because of the missing information. Now, what we can do is that we can consider two sets here. So let's say that f is a function that goes from 1, 2, 3, 4, and that goes to 1, 2, 3, 4, 5, and 6. And that is defined as f of x is equal to x for all x. And g is a function that goes from basically this set, which is 1, 2, 3, 4, 5, and 6. And this goes to 1, 2, 3, 1, 2, 3, 4, 5, and 6. And g of x is defined as x for x is equal to 1, 2, 3, 4, and g of 5 is equal to g of 6 is equal to 5. Now g of basically under f and g, then you can say that g of x, or GOF of x, you can say that GOF of x is equal to x for all x, which shows that GOF is 1, 1. It shows that GOF is 1, 1, but G is clearly not 1, 1. And to show you this example using Venn diagrams, or basically arrow diagrams, so let's say that f is a function from 1, 2, 3, and 4, and it goes to 1, 2, 3, 1, 2, 3, 4, 5, and 6. And then the other function goes from this function to 1, 2, 3, 4, 5, and 6. And the rule of f of x is basically f of x is equal to x, meaning that basically f is a function here. F is a function here that goes from f of x is equal to x would be this situation over here. So these are the mappings that we have under f from this set to the next set. Now under g, which is the other function here, we have g of x is equal to 1, 2, 3, 4. So that means that you have 1, 2, 3, and 4. And then the rest of these elements, f of 5, f of 6 is equal to 5. So this is mapped to this one, and this is also mapped to this one. And so because of these two, of course you can see that G is not 1, 1. G is not 1, 1. But then you can see that GOF, which is the function that goes from, let's say, this function all the way up to this function, GOF is basically 1, 1, because 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3, and 4 is mapped to 4. Which means that you can say that GOF of x is equal to x for all x. So that means that GOF is 1, 1. But as you can see, G is not 1, 1, and so one important thing to note here is that basically you have basically under F you have two sets over here. In these two sets, basically all of these elements must be covered, must be mapped to something. Otherwise F cannot be a function, and it's not. And well, the function does not have to be. It does not have to be surjective. Even if it's not surjective, it's still a function. It's a surjective function, meaning that what I mean to say is that f right here is a not surjective function, meaning that 5 and 6 are left alone under f. They are not the images of any of the elements in the first set over here. And as you can see again under g is not a surjective function, meaning that 6 is left alone here. And well, the function could be 1, 1, it could be not 1, 1. As you can see, f here is 1, 1. Every element of the first set has, every distinct element of the first set has distinct elements in the second set, or distinct images in the second set. But then G is not 1, 1, because there are two elements of the first set under G that do not have basically distinct images in the second set under G. So G is not 1, 1, it's not surjective. F is 1, 1, but it's not surjective. But then FOG, which is f of basically G of f of x. So you can call this one, for example, f of x. You can call this 2 f of x3. You can call it f of x4. You can call it f of x. So then G of f of x is basically this element over here. So you can say that basically this element over here, you can call it f of x. And on the other hand, this element over here, you can call it G of f of x. And to be mathematically correct, you can say that this is f of 1 and this is G of f of 1. This is G of f of 1. This is f of 2. This is G of f of 2. This is f of 3. This is G of f of 3. This is f of 4. This is G of f of 4, and so on and so forth. And so as you can see, it's not necessary that both f and g are basically 1, 1 for GOF to be 1, 1. GOF can be 1, 1 even if basically at least G is not 1, 1, right? So these are again the examples that we need to understand, because they all lead us to definitions, and those definitions are all based on these examples. And so and then as another example, example 21, we have basically our f and g both necessarily onto if g or f is onto. Our f and g both necessarily onto if GOF is onto. So over here we are talking about GOF being 1, 1 and asking if f and g have to be necessarily 1, 1 for GOF to be 1, 1. And here we are asking the same question about GOF being onto, and if for that to happen, f and g have to necessarily be both onto, right? So let's see how we can consider that. So for example, you can consider f as a function from 1, 2, 3, 4. 1, 2, 3, 4 to 1, 2, 3, 4. And g is a function from 1, 2, 3, 4 to 1, 2, 3 to 1, 2, 3, defined as f of 1 is equal to 1 and f of 2 is equal to 2, f of 3 is equal to f of 4 is equal to 3, f of 3 is equal to f of 4 is equal to 3. Now g of 1 is equal to 1. G of 1 is equal to 1. G of 2 is equal to 2. And g of 3 is equal to g of 4 is equal to 3. G of 3 is equal to g of 4 is equal to 3. So that means that you have these sets over here, f from this set to itself, 1, 2, 3, and 4. And then you have 1, 2, 3, and 4. And so you have f of 1 is equal to 1, and f of 2 is equal to 2, and f of 3 is equal to f of 4 is equal to 3. So as you can see, of course f is not, and this is basically f, and this is f here, and f is not 1, 1, and is not onto. So f is not 1, 1, and f is not onto. And then g is basically from this set to 1, 2, 3. And so as you can see, g of 1 is equal to 1, g of 2 is equal to 2, g of 3 is equal to g of 4 is equal to 3. And this is g over here, and as you can see, g is not 1, 1, and g is basically onto or surjective. And as you can see, and FOG is basically some function going from this set to this set. This is FOG, right? So as you can see, that means that, well, actually this is GOF, right? This is GOF, not FOG, but GOF. This is GOF, right? So that means that GOF of 1 is 1, GOF of 2 is 2, and GOF of 3 is equal to 3, and GOF of 4 is equal to 3. That means that GOF is 1, 1. GOF is onto. Right? GOF is actually onto. Because it goes from this set to this set, and all the elements of this set are the images of some element in the domain of the function. And as you can see, f over here is not onto, right? F over here is not onto, but in spite of that, GOF is actually onto. So then you can say that it can be seen that GOF is onto, but f is not onto. So you need to pay attention to the fact that over here, when we were talking about 1, 1, here we showed that GOF could be 1, 1, could be 1, 1, considering the fact that G is not 1, 1. So if G is not 1, 1 and F is 1, 1, still GOF can be 1, 1, right? So the second function, which is G, is not 1, 1. The first function is 1, 1, but still GOF is 1, 1. Now when it comes to this case over here, as you can see, GOF is onto, in spite of the fact that basically the first function, or f, is not onto, right? So when it comes to onto, it's possible that the first set is not onto, but then GOF is onto. When it comes to 1, 1, it's possible that the second set is not 1, 1, but still GOF is 1, 1, right? So this is what you learn from these two exercises. Now let's see. Now let's see what we have in question number 21. Or we have a remark over here. We have a remark over here. It says that it can be verified in general that GOF is 1, 1 implies that F is 1, 1, right? And so this is important to note. So here we said that here basically this exercise was about being onto. This was about being onto. This was about being onto, and this was about being where was number 20? This was about being 1, 1, right? Now, so then you can say that basically it can be verified in general that GOF is 1, 1 implies that F is 1, 1. So GOF is 1, 1 implies that F is 1, 1, as you can see over here. And we saw that over here basically G was not 1, 1, but F was 1, 1 and GOF was 1, 1. And we are saying that GOF is 1, 1 implies that F is 1, 1, right? So, and basically the meaning of this implication must of course be understood. So we can say that it can be verified. It can be verified in general. In general that GOF is 1, 1. GOF is 1, 1 implies that F is 1, 1. Meaning that wherever you see that there is some function F, there is some function G, and if depending on those two functions GOF is defined and it exists, then if GOF is 1, 1, that implies that F is 1, 1. That means that is necessarily the case, right? Now you can and what that means is that in the exact same situation, well, G could be 1, 1 as well, but you just simply don't know it. It could be on 1, it could be 1, 1, it could not be on 1, 1. But if you have two functions F and G, and if depending on those two functions F and G, then basically GOF is defined and it does exist, then in that case, if GOF is 1, 1, then you can conclude that basically F is necessarily 1, 1, meaning that you actually know that F is 1, 1, right? Now, and similarly you can say that GOF is onto implies that G is onto. implies that G is onto. And you saw that over here basically we have two functions f and g, and based on depending on those two functions in this particular case, of course, GOF is defined and it exists, and GOF happens to be onto, right? GOF does happen to be onto, and that implies that basically G is onto, and that's basically what we are saying over here. Similarly, GOF is onto implies that G is onto. Of course, it's not safe to conclude based on just one example that it's not safe to conclude based on one example that well, what I mean to say is that I wanted to say to make a statement, but then, as I was saying it, I realized that it made no logical sense. And but what I mean to say is that suppose that basically you have two functions here, f and g, and depending on those two functions, and depending on the way that those two functions are constructed, GOF is defined and it exists. Okay? So now it so happens that GOF in this case is 1, 1. As you can see, 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3, and 4 is mapped to 4. And of course, it's not surjective, it's not onto. And again, as it so happens, basically, F is 1, 1, right? F is 1, 1. So what that means is that, and based on this, now of course not based on this alone, but based on this situation, we have said that in general, it can be verified in general that GOF is 1, 1 implies that F is 1, 1. It's this exact situation over here. Now, it doesn't, basically the statement that we have made down over here, it doesn't mean that this statement, it doesn't mean that this statement is just based in this one, based on one simple case. It's just that if basically the function f and the function g exist, and then based on them the function GOF does exist, and the function GOF is 1, 1, meaning that the only way that the function GOF can be 1, 1 is that the function f at least is 1, 1. There is no other way, right? I mean, there is no other way that you can do it. Meaning that you can try to make the function f not 1, 1, and then try all the different possible cases, and then you will come to the conclusion that for GOF to be 1, 1, at least f has to be 1, 1. Now g, as you can see over here, is not 1, 1, and as basically as it so happens, it's just not important. G could be on 1, it could be not on 1, it doesn't matter. As long as f is 1, 1, then GOF can be on 1, can be 1, 1. And there is no other way to do it. And therefore, based on that, I can say that if the function f and g exist, and based on them, the function GOF exists, then the function GOF is basically 1, 1. The function GOF can only be only be 1, 1 if the function f is 1, 1. And therefore we are saying that the function in this situation, the function GOF being 1, 1, implies that the function f is 1, 1. Meaning that in all such cases where the function g of f is 1, 1, then the function f has necessarily has to be 1, 1, right? So that's what I was trying to say. Now in the same manner, we have the function, we have these two functions over here, f and g, and you can see that the function g of f based on f and g does exist, and it is onto, it is surjective, because all of these elements in the third set over here is the image of some element in the domain of the function. Now you can see that, of course, the function f over here is not onto. There is this element over here which is not the image of any element in the domain of f, so f is not onto, or it's not surjective. But g is surjective. Now this situation we can summarize it as two functions f and g existing, and based on those two functions, the function g of f is defined and exists, right? Now g of f happens to be onto. Now g of f in this situation can only be onto if the function g is onto. Now the function f could be onto, it could be not onto. That goes into the different cases that can happen that we don't know about. But what we know is that function g necessarily has to be onto so that the function g of f is onto. There is no other way. And it makes sense because imagine that the function g is not onto, right? If it's not onto, then that means that there is at least one element in the domain of g, in the codomain of g, that is not the image of some element in the domain of g, which is this second set over here, right? Now what that means is that now if that happens, then there is some element in this third set over here, which is the codomain of g of f, which is not the element of any, which is not the image of any element in some other set, either the second set or the third or the first. It doesn't matter really right now. And so when that happens, that simply means that g of f is not onto. So so then you can say that if g of f has to be onto, then g has necessarily has to be onto. And that's basically why we say that similarly g of f is onto implies that g is onto. Implies that g is onto means that if g of f has to be onto, then g necessarily has to be onto. Implies means that when we say implies that g is onto, what that means is that g necessarily has to be onto. There is no other way, right? And if you don't understand the meaning of implication, let me give you an example in order to understand it. Okay, so now in order to understand what it means to say that something basically implies something else, let's take a simple example. So for example, first of all, when we say that when we say that basically A implies B, when we say A implies B, or when we say P implies Q, what that means is that, let's consider this one, P implies Q. What that means is that if P is true, then Q necessarily must be true. What that means is that if Q is not true, then P cannot be true. Or another way to say the same thing is that in order for P to be true, Q necessarily has to be true. So for example, let's take the example of basically a number. So for example, let's say that, for example, 6 is a multiple of 2 and 3. And I'm using the connective and here, meaning that 6 is the multiple of 2 and it is a multiple of 3, both at the same time. So then I can and then based on this statement, what I can say is that, so of course then, for example, you can see that if I multiply 6 by 2, I will get a 12. 12 is a multiple of which is a multiple of 6, which is a multiple of 6. So what that means is that now 12 is a multiple of 6, and as you can see, it is a multiple of 2 and a multiple of 3. At the same time, simply because the way that we got 12 was we generated 12 out of 6 by multiplying 6 by some number, and it doesn't really matter what that number is, but as long as you generate that number using some number, then all the properties of that number in terms of multiples will be transferred to the new number, meaning that now the new number, whatever that happens to be, is a multiple of 2 and also multiple of 3, because 6 was a multiple of 2 and a multiple of 3, right? So now suppose that now if I prime factorize 12, I will get 2 times 6 and 2 times 3. That means that 12 can be written as basically 2 times 2 times 3. Suppose that I take out this factor of 3 from 12, and I'll be left with a 4, right? If I divided 12 by 3 to take out that factor, I'll be left with a 4. And as you can see, 4 is not a multiple of 4 is not a multiple of 6, right? But 12 is a multiple of 6, and 12 is a multiple of 2 and a multiple of 3. So I took out the multiple of the factor 3, and now 12 is not a multiple of 6 anymore. Now, so based on this whole situation, I can say that if a number is a multiple of 6, then it is a multiple of 2 and 3. The same statement I can write it as if a number is a multiple of 6, then it is a multiple of 2, and it is a multiple of 3. So what this statement means, and we know that this statement is true based on what we said over here, a number simply cannot be a multiple of 6 if it's not a multiple of 2 and if it's not a multiple of 3 at the same time. which means that if a number is a multiple of 3, then it is necessary that that number is a multiple of 2, and it's also necessary that that number is a multiple of 3. Then based on this situation, I can say that a number is a multiple of 6 implies that that the number is that the number is a multiple of 2, that the number is a multiple of 2, and the number is a multiple of 3, right? So I'm using the word and here, the connective and, meaning that both of these has basically that you can that both of these have to be true at the same time, so that the number is a multiple of, and that the number is a multiple of 6. But then now, based on this, you can say that if you see a number which is a multiple of 6, then basically if you see a number that, if you encounter a number and if you know that the number is a multiple of 6, then you can with 100% certainty say that, then you can say with 100% certainty that basically the number is a multiple of 2. Or you can say with 100% certainty that the number is a multiple of 3. Or you can say with 100% certainty that the number, of course there is no of here, you can say with 100% that the number is a multiple of 2 and 3. So that's basically the meaning of this whole story there. So that is the meaning of multiplication. So here we said that if you encounter a number and you know that the number is a multiple of 6, then you can say with 100% certainty that the number is a multiple of 2, or the number is multiple of 3, or the number is multiple of 2 and 3, both at the same time. And you can say that, or all of those things, or any of those things, because a number is a multiple of 6 implies that the number is a multiple of 2 and the number is a multiple of 3, right? So that is basically the meaning of implication. So coming back to the example that we had before, we said that basically if we have a set over here, set A and set B and set C, and we have basically f over here, and we have some other function g over here, and we have another function GOF based on f and g, the composite function GOF, then you can say that basically the function GOF is onto, then you can say that the function GOF is onto is onto implies that G is onto. So what that means is that if the function g of is onto, if I know that the function g of is onto, then I can say with 100% certainty that the function g is onto, because when I say implies, if this has to be true, then this part necessarily has to be true. There is no other way, right? Now, of course, I'm not talking about the function f here. I'm just talking about the function g here, meaning that in this situation, if g of is, suppose that g of is onto, then you can say that f could be onto or it could be not onto. That I don't know. There is no way for me to say that, because in some cases it could be onto, in some other cases it could be not onto. But if I can make sure that g is onto, then I can say with 100% certainty that g of will be onto. And so then based on that, I can say that if g of is onto, then g is necessarily onto. And another statement that we said before was that the function basically FOG, or GOF, I'm sorry, GOF is 1, 1 implies that f is 1, 1, right? So what this means is that now if I have the same situation and I know that basically g if basically 1, 1, I know that g of is 1, 1, then f has to be 1, 1 so that g of can be 1, 1. There is no other way. Now g, I'm not talking about g here in this second situation. G could be 1, 1, it could be not on 1, I don't know about that. But whether g is 1, 1 or whether it's not on 1, that doesn't really matter, because in some cases g is 1, 1, in some other cases g is not 1, 1. But provided that g exists in such a way that g of can exist, and provided that f exists at the same time as well, then provided that f is 1, 1, then basically g of will be on 1, or g of will be 1, 1. So then again, I can say that the function g of is 1, 1 implies that in this particular situation, having all of this configuration all together, when I know that g of is 1, 1, that implies that f is 1, 1. Meaning that if f is not 1, 1, then there is no way that g of can be 1, 1. Right? That's the meaning of implication. Now, there is something that we did in one of the previous videos, of course, that we were talking in the beginning of this section related to these composite functions and the composition of functions. We came up with the situation. We introduced the situation in order to understand the concept of composition of functions. And we said that we had all of these, set A, for example, and these were some student names, and they took part in a board examination. Now the board examination gave them some roll numbers in that examination, meaning that the student was given a roll number, right? And let's call this set B, for example. These roll numbers, you could imagine that they are basically a subset of the set of natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on and so forth. And of course, no two different students will be given the same roll number, because then otherwise everything will be messed up. So every single student, every distinct student from the set A will be given a distinct roll number in the set B, and that can be basically shown with a function. For example, f from A to B, that it takes a student name and then it gives you a roll number as the roll number of that student, right? And then what we did over here was that we said that basically this roll, and because there could be problems here, meaning that, and then this roll number has to be written on the question paper or basically on your answer sheet. Now the answer sheet will be then, after once the student takes the examination, the answer sheet of course will be given back to the board, and the board has to give those answer sheets to some examiners, not examiners exactly, but to some people who will correct those papers. So those papers will be corrected by those people, and those people, if they know their roll number of the student, they could do something in favor of that student if they happen to know the student, right? So now in order to prevent that from happening, what we can do is that basically the board decides to deface those roll numbers on the answer sheets and replace them with some code numbers. Meaning that they will think of some code numbers, some numbers essentially subsets of the set of natural numbers. Again, 1, 2, 3, so on and so forth. But now here the point is that the student doesn't know his code number. He knows his roll number. He doesn't know his code number. Once the student hands in his paper and his or her paper and leaves the examination hall, then the board, what they do is that they deface those roll numbers and basically replace them with a code number. And the student simply doesn't know what code number is going to be printed on his paper instead of the roll number, and the roll number will be simply distracted. It basically will be simply not there anymore. I mean, the people that correct the papers will not see the roll number anymore. It's just not there anymore. It's simply erased, right? And then what the board people will do is that every roll number is given to a code number, meaning that through some other function G, for example, what they do is that every roll number will be assigned to some code number. Now, the paper correcting people, the people that correct the papers, they correct the papers. They write those. They write a mark. Basically the marks a score based on the answers in the paper, whether they are correct or not, and so on and so forth. And that mark will be assigned to some code number, meaning that what the examiner does is that he simply has a paper. He is correcting a paper. On top of this paper, there is some code number. And then he corrects that paper, and then there is a score relative to that paper. So that score will be related to some code number. So what he can do, so suppose that, for example, the person that corrects those papers, he corrects, for example, 20 or 30 papers. Then he can basically form a table of some code numbers and some scores. He gives that table to the people from the board. And the people from the board know basically that, for example, this particular code number is related to that particular roll number. So then that score will be related to some roll number. Again, the board people know that this roll number is related to this basically specific roll number is related to some specific student. So then that score, which was related to that specific roll number, will be basically given to a specific student, and then that way, after going through basically the inverse of G and the inverse of F, going in the opposite direction, then a student gets a score. That's basically how they do it, right? So as you can see, first what happens is that through function f, a student will be assigned a roll number. Then through some function g, a roll number will be assigned some code number, right? So that is basically in the first stage. These two things happen in succession. Now in the second stage, once they want to assign that score back to the student, what they have to do is that they have to basically go in the other direction, meaning that the code number has to be assigned back to a roll number, and that roll number has to be assigned back to a student name. And so now let's go through the text here and see how they do it really. Okay, so basically now we would like to, so now what the text says is that now we would like to have a close look at the functions f and g described in the beginning of this section in reference to the board examination. So each student appearing in class 10 examination of the board is assigned a roll number under the function g. So each student appearing in class 10 examination of the board is assigned a roll number under the function f, and each roll number is assigned to a code number under the function g. After the answer scripts are examined, examiner enters a mark against each code number, as we described here. Examiner enters a mark against each code number in a mark book and submits to the office of the board. So the board officials decode by assigning roll number back to each code number, code number. So the board officials decode by assigning roll number back to each code number through a process reversed to G, and thus mark gets attached to roll number rather than code number, right? Further, the process reversed to F assigns a roll number to the student having that roll number. Now this helps in assigning mark to the student scoring that mark. So we observe that while composing f and g, to get g o f, first f and then g was applied, while in the reverse process of the composite g o f, first the reverse process of g is applied, and then the reverse process of f. So what that means is that, so this last part is important, and what that means is that basically what it's saying is that we observe that while composing f and g, to get GOF, first f and then g was applied. First f and then g was applied. Meaning that first you have to get, basically first you have to apply f, and then suppose that you have some x over here, then you will get f of x over here, and then if you apply g to f, you will get g of f of x, which is the same thing as GOF of X, right? So basically, while composing F and G to get GOF, first F and then G was applied, right? Now, while in the reverse process, and the reverse process refers to basically the process in which basically the mark was attached to a code number, then we wanted to attach the mark to a, or the score to a roll number, and then back to a student name. So in the reverse process of the composite GOF of the composite GOF, first the reverse process of G is applied. First the reverse process of G is applied, and then the reverse process of F, and then the reverse process of F. So these two are important here. Now, I'm going to end this video here, and in the next video we will continue with these examples. There is a couple more examples, some definitions and some theorems and so on and so forth, and then we will get to some exercises. So I will see you in the next video, and thank you.